All right, so the next discussion of 4.3 is all about where a graph of a function lives with respect to its tangent lines. And so this is actually something that can tell us a bit about the function, and we can use it to also help establish maximum and minimum values. So that's kind of one of the most helpful things about it, and that'll be in the form of the second derivative test. So the first idea is concavity. So if a graph of f of x lies above all its tangent lines on I, we say it is concave up on I. And so the picture is down here, concave up. If you choose any kind of point and draw on a tangent line, your graph is going to be above that, and we're going to say it's concave up at that value, or on that interval. And then if f of x lies below all its tangent lines on the interval, we say it's concave downward. So the picture is going to, again, be like that. So again, concavity has to do with where a graph of a function is with respect to its tangent lines. So concavity really, really has to be tied to the geometry of what's going on. Okay, so a definition is inflection point. So a point P on a curve is going to be called an inflection point if f is continuous near that point and the curve changes concavity. So what happens is, if we look at all these examples we have written here, is, well, the concavity up to this point is going to be downward for this first one, and then the concavity of the graph changes to be kind of upward after this point. You can kind of view it like that. And for this one, again, it's going to be kind of downward. The graph is going to be below its tangent lines. And then once you hit this point, after that, the graph is going to be above it. And then for this one, again, well, what we're going to have is it's going to be below or above all its tangent lines. So this is going to be concave upward. And then the tangent lines are going to be above. So it's going to be concave downward. So again, inflection point is a point on your graph where the concavity of everything changes. Okay, so we have a concavity test, very much like we have increasing and decreasing tests. In fact, you can think of the concavity test as a test for increasing and decreasing, but of the derivative of the function instead of the function itself. What we mean by that is, if you think about the way the derivative is changing, if you think of the way these tangent lines, the rate of change, then what we're going to do is we're going to see, are they getting bigger or are they getting smaller? And what I mean is the slopes of the tangent lines. So, for example, if we draw this tangent line and I pick another point, I'm still going to be positive tangent line, but it's starting to get flatter and flatter. That means that the slope of the tangent line is decreasing, or the derivative is getting less and less. And then similarly here, we start out with a negative steep slope, and then it gets less steep. So in this case, it's increasing. So what you want to take away from that is the derivative of the derivative has a positive rate, or the second derivative should be in this case, should be decreasing because the derivative of the derivative is getting smaller. And in this case, the derivative of the derivative is getting bigger. It's increasing. And so what our concavity test says is, if f double prime of x is greater than 0 on I, or for all x in I, then the graph of f of x is concave up on I. So again, if the second derivative is larger than 0, then it's going to be concave up. See how we're concave up? And then if the second derivative of x is less than 0 for all x in I, then the graph of f of x is concave down. On I. So again, that's the case we're having here. And so if you want to think about what's happening here in terms of what these inflection points are, is, again, just think about an inflection point as, well, you're applying the first derivative test, but to the derivative of the function itself. It's where the second derivative changes sign. So this is going to be negative to positive, and this is going to be second derivative positive and changing to negative values. So you can see it like that. So you can think of inflection points as kind of maximum and minimum values of your first derivative. Now we come to the second derivative test. And what the second derivative test is going to tell us is we want to assume that our second derivative of our function is continuous near c. And the first case is going to be that the first derivative at c is equal to 0. So c is going to be a critical number. Our second derivative is smaller than 0, so these two things, then our function value at c is a local max. And so the case that we have here, it's going to look like this. And we know that at this value c, your function value or your derivative is going to indicate a flat tangent line, and the tangent line is going to be above your graph. It's going to be concave downward at that point. So that's what these two things tell you. And then what you can determine from that is that it has to look like this. It has to kind of have this hill shape to it. And so that's what the second derivative test tells you. And it's very intuitively clear that that's what you should have, because you know the tangent line has to be flat and it has to be above the function. So you should get a local maximum. That's higher there. And then the second one says, well, if f of c or f prime of c is 0 and f double prime of c is greater than 0, then f of c is a local min. And so the case you're going to have there is going to look like this. And this is c. So here you have that the tangent line is going to be flat and the graph lives above the tangent line. So it has to be a local min, and that's the picture you want attached to it. Now, one thing you want to be careful of is if this is equal to 0 at that point, if f prime of c is also equal to 0, then it's inconclusive. You might have a local min, you might have a local max, but we have to use something else. So that's not going to help you. So that's where the second derivative test can fail. But one other thing I want to point out about the second derivative test is notice it involves 3 pieces of information. Here, we need to know that at that c, our derivative, first derivative, is 0. We need to know the sign of the second derivative, and then we can use that to determine what this value for your original function is. So because 3 different functions are floating around, the original function, the derivative, the second derivative, make sure you get those kind of in order, and make sure when you're working out these problems, you have it clearly kind of worked out. So bookkeeping is very, very important for these problems. So the next example, we want to take a function, and it's just going to look like this. You're going to have f of x equals x to the 4th minus x to the 3rd. And we want to get an idea for what its graph looks like. Now, what I'm going to do is, because I know this video series is getting kind of long for this section, what I'm going to do is I'm going to finish up with this example here, and I'll probably make another video about examples of graphing functions, especially because section 4.5 is also going to involve graphing functions. And so what we're going to do is we'll finish up this section with this, but if you want to see more examples, there will also be a video posted with more examples of graphing functions. You may want to have watched 4.4 to watch some of those examples, but I'll indicate which ones involve 4.4 and which ones don't. And really, it's just going to involve kind of that last bit where we're going to talk about kind of the end look of these functions. But you don't need 4.4 to do this one. Okay, so what are we going to do? What we want to do with this is we want to start by, let's find critical numbers, maybe some inflection points, and max min values, and all that jazz. Okay, so here's kind of a solution. So if we want to start, we want to take the derivative, and if we take the derivative of this function, we're going to get 4x to the 3rd minus 3x squared. And we also want to take the second derivative. We're going to use information from all of these pieces here. Okay, so this one's going to be 12x squared minus 6x. And I could actually kind of factor these because that might be helpful. So I'm going to get 4 times x, sorry, not 4, x squared times 4x minus 3. And then if I factor this one, I'm going to get, I can actually pull out a 6. 6x, 2x minus 1. And I can even factor this too, if I pull out an x to the 3. I'm going to get x minus 1 there. So this is kind of their forms, and then their factored forms. Notice taking the derivative of it unfactored is a little bit easier than taking the derivative of the factored version, because I don't have to use the product rule. So let's start by finding critical numbers. So what are critical numbers? Critical numbers are going to be where your function is either or the derivative of the function is either undefined or equal to 0. Well, the derivative of our function is a polynomial. It's never going to be undefined, it's defined everywhere. So we want to look for where f of x is equal to 0. And so what that's going to imply is that x squared, 4x minus 3, is equal to 0, and that's going to be when x is equal to 0, and also when x is equal to 3/4. So you get those two values. And I apologize, my chili is burning, so I'll be crisis averted. Okay, so critical numbers when your derivative is equal to 0, or when your derivative is undefined. But our derivative is defined everywhere, so we're not going to worry about that. So these are going to be the critical numbers. Okay, now let's find inflection points. Inflection points. We haven't done this yet in an example. So inflection points, what you want is those are going to be values where your derivative is going to, or your second derivative is going to kind of change from positive to negative or negative to positive. And so if we think of the second derivative as a function on a number line, that's going to be where it's going to cross the x-axis, or potentially where there's an asymptote on this function. So again, you want to look for kind of these critical numbers of the second derivative, and then you want to apply the first derivative test. So find critical numbers of f prime and apply first derivative test to f prime. So remember, you're applying all this stuff to the next level down, not the original function, the first derivative of it. So we want to find the critical numbers of f prime. That means we want to set f double prime equal to 0. So this is 6x, 2x minus 1. And you're going to get that x could be equal to 0, or you're going to get that x could be equal to 1/2. And so what I'm going to do is the points of inflection. If I look at this, I'm going to get 0 and then 1/2. And if I build myself a little table here where I choose x's and I choose f double primes of x, kind of those values when I plug it into the second derivative. Well, if I choose a value kind of to the right of or left of 0, maybe -1, I'll use kind of bigger lines to indicate these things here. -1, well, if I plug in -1, I'm going to get 6 times -1 times 2 times -1 minus 1. Again, this is going to be a positive times a negative times a negative. So that's going to be greater than 0. So you're going to get that your second derivative is positive during that time. So the concavity is upward. And then if I choose a value between 0 and 1/2, maybe like 1/4, plug 1/4 in, you're going to get 6 times 1/4 times 2 times 1/4 minus 1. This is going to be a positive times a positive, but if I take 1/4 of 2, that's going to give me 1/2 minus 1, that's going to be negative. So this is positive, positive, negative, that's going to be less than 0. So I know in this range, you're going to go negative. And now I can kind of see that, yeah, if I plug in x equals 1/2, I should get positive, positive, positive. Sorry, not 1/2, maybe 1. If I plug in x equals 1 to there, I should get 6 times 1 times 1. So that's going to be positive. So I'm going to get positive. So these are actually points of inflection because the concavity changes at them. And there's not going to be any other points of inflection. This is important because this is an always continuous function. And if it's continuous, then what you're going to have is it would have to kind of change. It would have to have a point in the x-axis where this function equals 0. But these are the only two values where that's true. And so, so we can't have a change from positive to negative. Okay, so now what we want to do is we found critical numbers, we found the inflection points. Now let's find the max / min values. Well, I can use the second derivative test to help determine that. So maybe I want to judge the critical numbers. What happens at x equals 3/4? Well, if I use second derivative test, I already know that if I plug in 3/4 to the derivative, I'm going to get 0 because I found that in my critical numbers. Well, what happens when I plug 3/4 into my second derivative? Well, I'm going to get 6 times 3/4 times 2 times 3/4 minus 1. And so this is going to be 6 times 3/4, 9/2, times, this will be 3/2 minus 1, or 9/3, times 1/2, or 9/6, if I did that correctly. But it doesn't actually matter if this is this exact value. What actually matters is we know that 3/4, 3/4, is greater than 2, so the second derivative is positive. We actually already figured that out. So what matters is that this is positive. And so what that tells us by the second derivative test is that here we know it's a critical number, and we know that the second derivative, the tangent line, has to be completely below your function. The function is above it, it's concave up. So this is f of 3/4 is a local minimum value. That means that it looks like this. This is kind of what it looks like. All right. Well, what about x equals 0? So we tried that one. Let's try this one. Well, second derivative test doesn't work. Inconclusive. And that's because even though when we plug in 0 to the first derivative, we get 0, when we plug in 0 to the second derivative, we also get 0. So this is kind of where it's inconclusive. So we have to use first derivative test. And so what we want to check is we want to see how this first derivative changes from the point 0. So let's pick a point, -1. And then we also have to pick a point between 0 and the next critical number. So we want to pick a point between 0 and 3/4. You don't want to pick just any point on the right of 0. So we have to pick maybe like 1/2. Okay, so let's see what happens at these test points here. So we have x and we have f prime of x. And if we plug in -1, well, remember f prime of x, it looks like this. X squared, 4x minus 3. So you're going to get a positive value times -4 minus 3 times a negative value. So this is going to be less than 0. So this is going to be negative up to 0. And then if we plug in 1/2, well, we're going to get a positive number, 1/2 squared, times what we're going to have is 1/2 of 4, which is going to give us 2 minus 3, which is a positive, times a negative, which is also less than 0. So, I don't know why I wrote positive there. So this is negative here, and this is negative here. And so there's no change. We have negative up to 0, negative past 0. And so at this critical point, no change. So what the first derivative test says is this is f of 0, not a local extrema. Food break. Okay, so the next thing we want to know about this function is which intervals is it going to be increasing or decreasing on. And we actually already have part of this information is if we kind of started to apply the first derivative test, we used it to determine that 0 is not a local maximum or local minimum. It's kind of that third case where there's no change. So we know that if we go x to the left of 0, that you're going to get negative. If we go x to the right of 0, but also before 3/4, you're also going to get negative. Well, now we want to know what happens to f after, something there. One thing we actually know is we do know that 3/4 is a local minimum. That means the function itself can't keep decreasing after that point. So this actually has to be positive. So we know that if x is greater than 3/4, you have to get positive values. And you can verify that by plugging a test point in if you want. But again, the conceptual thing is we know this is a minimum value. So our function itself can't keep decreasing at that point. So what we know is we know that it's going to increase from -∞ all the way up to 0. It's also going to it's going to decrease from -∞ all the way up to 0, but also from 0 all the way up to 3/4. And there's actually a convenient way of writing this. We can just write it as one interval from -∞ to 3/4. That's where it's going to be negative. Even though it's equal to 0 here, it kind of stops there. What it's going to look like is it's going to look like something like this, where it's going to kind of have this flattening out point, but it's going to keep decreasing. And it's still going to be decreasing on this interval. And then the interval of increase is going to look like this. Well, it's going to be everything after 3/4. up to infinity. And so those are going to be the increase and decrease. Okay, so the last step in this example is we want to put all of this information together. So again, we know the inflection points are at x equals 0 and x equals 1/2. We know the maximum and minimum values, the minimum at x equals 3/4, and we have no maximum values. And if I plug that in to my function, so remember this is my original function, so what I get is 3/4 raised to the third times 3/4 minus 1. So again, this is 3/4 raised to the third times 3/4 minus 1. You get this, and we get negative 27 over 256. And then we also know that it decreases from negative infinity all the way to 3/4, and that it increases from 3/4 to infinity. So we're going to see that at play here. A couple other things you want to keep track of is we can find the x-intercepts of the graph. That's going to be where it crosses the x-axis. You can also find the y-intercept. That's going to be where it crosses the y-line. So when x is equal to 0. So this is where your function is equal to 0. Well, if our function is equal to 0 and our function looks like this, x cubed times x minus 1, this means x is going to be equal to 0 or 1. So we know our graph is going to cross at the origin, and then also at, I'll put 1 over here, just to kind of indicate that, so to balance it out. And 1 over here. Okay, so this is 1. And then the y-intercept is going to be when you plug in 0, and in this case we're going to get 0, so we actually already have that written there. And then the last piece of information we want is end behavior. And this is going to be the limit of your function as x goes to infinity. And this is actually going to be about what all the next section is going to talk about, is the end behavior of functions. What happens when you take the limit as x goes to infinity, and how to determine that for more functions than we've been able to. Although, in this case, what we know is it's a polynomial, and it has a positive leading coefficient, so this is going to be infinity. And then we also want to know the limit as x goes to negative infinity. This is the negative end behavior. And since it's an even degree, this is going to be the same as going off to infinity, and so it's going to be infinity. So it's shooting up as we go out x in both directions. Okay, so what do we have here? We want to kind of plot these parameters. So we know that, maybe here's 1/2. That's going to be kind of an important x value. And then in between 1/2 and 1, you're going to have 3/4. And we know our function kind of hits its minimum value there, or at least a local minimum value there. And this is going to be negative 27 over 256. So keep in mind, it's not to scale. That's okay. We're just getting an idea of what the picture looks like. And we know it crosses here, so it's going to hit this minimum and cross the x-axis there. And then we know because of the end behavior, as you go out x, it's going to shoot off to infinity. So this is off to infinity. F of x goes to positive infinity. It's going to shoot off that way. And we know that it's going to come up and cross this line here, or this at the origin here. But one thing we want to keep in mind is that there's a point of inflection at 1/2, and there's also a point of inflection at 0. And so how that's going to look is we know from 0 off to infinity, or negative infinity, it's going to shoot up like that. And then the point of inflection, since your graph is going to be kind of a below or above the tangent lines, you can see that here, it's going to switch and be below the tangent lines. And that's what happens when it crosses 0. And then at negative, or at 1/2, it's going to kind of change that course again. So it's going to be decreasing, and then it's going to kind of start going this way. So if you can kind of see that, it makes that change at 1/2. So just to kind of drive home that point is we have these changes at 0 and then also at 1/2 where the concavity of the function changes. So that gives you these different values. And maybe you're wondering, okay, how did I know the concavity of the function over here? You can just pick a test point. So you can just pick a test point. I believe we did that in our work. I don't have it written up here, but pick a test point and find out what the concavity of this is. You plug it in to your second derivative, say -1, plug it into your second derivative, and you should get something positive. So again, if we plug in -1 to this, yeah, we're going to get something positive. So it tells you that the concavity is up. And then we know at 0 it's going to switch, so it has to go to concave down, and then at 1/2 it's going to switch again to concave up. And then it stays concave up throughout those. So that's kind of how you pull it all together. I'll make a video with much more or many more examples, but I hope that was exciting.